Hello friends, welcome to follow up. In this video, I'm going to analyze problem 1457, Pseudo Palindromic Paths in a binary tree. Our plan is to present three formats of solutions. The first one will be the most natural and verbose one, and then we are going to optimize to make it more compact. So we are going to use dictionary, set, and bitmask, or the last one, bit operations, to represent the procedure. So with that said, first I'm going to digest the problem requirement, and then we are going to do the analysis, and in between we write some code. So with that, now let's first move to problem digest. So here we are given a binary tree, and the node values are digits, right? So we see a path in the binary tree is pseudo palindromic if at least one permutation of the node values in the path is a palindrome. So in other words, if we can arrange the corresponding path list to be a palindromic list, then it's a pseudo palindromic, right? So we want to find the number of pseudo palindromic paths going from the root node to leaf nodes, right? So here the path means root to leaf path, right? So actually, if you see this problem statement, basically you will naturally come into two thoughts. First, we need to find the root to leaf path. That's the one thing. And the second, we need to be able to check if a path is pseudo palindromic, right? So with that said, let's look at the examples. So the last example is very special because it's just single node. It's naturally a palindromic. So we are going to return 1. In the first example, if you look at the three paths from root to the leaf, so you have 2, 3, 3, 2, 1, 1, and 2, 3, 1. So there are two of them can be arranged to be palindrome. So for example, this one you can have 3, 2, 3, and this one you can have 1, 2, 1, right? So this output is 2. And then for the second one, you can interpret. So 2, 1, 1 is the pseudo palindromic one. So the output is 1. So also we want to notice that the problem set is decent large, right? The number of nodes can be up to 10 to the power 5. So with that said, let's look at the analysis. Here first I want to mention that so for a list containing digits to be pseudo palindromic, so it's equivalent to see that there is at most one odd frequency. For example, in this path 2, 1, 1, so 1 appears twice, the frequency is 2, but 2 appears once, the frequency is just 1, right? The reason is very easy to understand, but you'd better to make a deeper digest. So for example, you have something like this. You have 1, say 2, 2, and 4, 4, right? You can do a lot of rearrangement to make it. So let's see, I put the 4, 4 in the two ends, 2, 2 in the end, then I put 1 here. So this corresponding, you have one odd frequency. If you do not have odd frequency, it seems much easier, right? Just evenly distribute all the unique numbers. So with that said, let's look at the solution. So first, we can do all those things together, right? Or separate. So basically, I can find the path and check validity, right? So for this, we can use dictionary, right? We can use dictionary to get all the unique numbers in the path and their frequencies, though this is a little bit verbose, but it's very natural, right? Very natural. So I'm going to first write a solution like this, and then I'm going to do two optimizations, right? Let's first write this one. So we want to find the root to leaf path. We need to use traversal. There are many traversals. You can freely use that, either iterative format or recursion, or pre-order, post-order, in-order, anyway. So, but here we want to find the root to leaf node. I'm going to use a depth first based traversal. So notice that we have at least one node, right? So we can always initialize a stack. Let's say we have our root, and then I'm going to use dictionary to record the pass information. So currently its root value appears once, right? So with that said, I can also initialize a result variable to be 0, right? So if the pass is valid, I'm going to increment the result by 1. Otherwise, we're going to not increment. So with that said, let's do the standard while loop. So while s, so we can get the node, we can get the pass information at s-pop. Then we want to check if the path is a root to leaf path. So if not node left and not node right. So this will be a root to leaf path. But if it's a good path, we want to also check if it's pseudo palindromic. So for this, because this path is dictionary, we just need to make sure if the odd frequency is at most 1, right? Let's check the odd frequency. We can use list comprehension, right? So we can sum. So this is the sort of iterator, right? For v, or for frequency in path values. So if frequency modulo 2 is not 0, right? It means it's odd, right? So if this number is less than 2, it means that the odd frequency is at most 1. And then we're going to not return result increment by 1. So this is basically a problem logic check. And then we can think of the standard traversal. So in this problem, we can either check the left subtree or we can check the right subtree, both are okay. So here I'm going to check the right subtree. If node right, then we're going to first get a temp as a path copy, right? As a copy. And then we want to modify it because now the root ended at node right. So we want to add this information. So we want to get node right value. So we're going to update that. So it's get node right value. So we're going to set default to be 0 if this not already in the dictionary, right? So increment by 1. So then we are going to do s append. So the node right, and then the path information. So this is the right subtree. So similarly, we can add the right subtree, left subtree. So we can do left. So here we can do left, and here left, and here left, right? So if we do not consider this this information or this if, so then the structure will be is nothing but a traversal, right? This is also a pre-order traversal. So and then we just need to return. So the result. So this is the one solution format. Let's first do a test. Yeah, it passes one example. Now let's look at. Yeah, it's fast enough, but I guess we use a lot of memory. So because here we store all those information, right? But if you imagine this, so we don't need to use a dictionary. We just need to use a set. So here I want to optimize to using set. The reason is that I just want to look at evenness or oddness of the frequency. So if a number, say in this example, say 211, so we have 2 if I add this set, right? Then I add 1. If I see 1 again, I just need to pop this 1. So I left just the 2. So the ones left will be the count of odd frequency unique numbers. Then we just count if it's less than 2, right? So this is actually similar to this one, but we save a lot of space. So now let me do this. I'm going to copy this part, and then I'm going to call this one version v1. So now here I'm not going to use dictionary, I'm going to use set, and then I have to do this, and then what I want to do here, the change will be if length of the path so it's less than 2, right? Because here I'm using a set to represent the length. then I'm going to increment the result. Then otherwise, what do we do? So then what we want to do is the following. So we have a copy, right? And then we want to check. So if a node right value, so it's in, right, in temp, then we just need to remove this value. So we're going to do temp remove node right value. So otherwise, it's not in this yet. So we're going to do temp add node right value, right? And then what we are going to do is we are going to append the same information here. So this is for node right. And similarly, I'm going to copy this part. And then I'm going to copy that, change this right to left. Then we can do a test. Yeah, it passes one example. Now let's look at the generic case. Run answer. Let me see what's the problem here. So we have a result. So so node pass. Yeah. So here I guess I forgot one thing. So I need to initialize this using the set containing root value. This is important, right? So now let's do a test again. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. It's fast enough, but still we are using many spaces. But here another thing, how do we check this thing? Here we are going to use set. So now I'm optimized to be using let's say using bitmask, bit or bitwise operation. And the thing is very straightforward. So if we want to see, so here the digits, the root values are digits, right? So we just think of num positions, right? So here we have num positions. So then you have a 2, right? If you have a 2 appeared in the second position, you are going to count it by 1. And then you have third position, 3 appears twice, you can make it 2. But because 2, we just care about evenness or oddness, you can make it 0, right? As long as you have a pair, you just make it disappear. But if you have 2, 3, 3, 3, then you are going to have another 1, right? Then finally, you just need to count the number ones in the bit positions to see if the odd frequency unique numbers are less than 2 or not. So, but in order to achieve this, we don't need to even specify this list. We can use bitwise operation. So the thing is that if you want to check if the S bit is set, so you can consider this, right? 1. So let's move to this right set by S. So or here I'm going to use node value corresponding to the I, right? Then I can do this. And 0 exclusive all with this number. So this number is nothing but 2 to the power of the node value. So it's nothing but 0 exclusive all with 2 to the power node value. It's just a fancy writing format. And this way, so if S bit is set, then you are going to get 1. If it's not, you're going to get 0. In other words, if it's even, you're going to get 0. If it's odd, you're going to get 1. If you can think of the currencies, right? So this is the case. Then each time, so for example, you have another one, 3 comes again. Then you are going to, what you are going to compute, for example, for this pass, first I'm going to have 0, right? And then I check with 2. So basically exclusive all is 2. 0 exclusive all with any number will be that number, so you get 2, right? Then I have 3, so I'm going to do 1 0 exclusive OR with 3. 3 binary representation is 1 1, right? Then in this way you are going to get 0 1, right? Then you have another 3, so you do 0 1 with 1 1, so you get 1 0. So overall, you know, so only 1 bit position corresponds to a set bit. So this means the number of odd frequencies count is 1, right? So in other words, this is a valid pseudo palindromic path. But if you see 2 3 1, let me check this path for you. So first you match 2, you do bit size exclusive OR with 2, you get 1 0, right? You get 1 0. And then you do this result with 3, you get 1 1. What do you get? You get 0 1, right? And then you have 0. So let's see. Yeah, you have 0 1. So 0 0, you have 1 0. 3 is 1 1. You get 0 1. And then you get 0 1 with let's see. Oh, here I think I explained not correct. So let me because we need to consider the power, right? So here first you have 0. So for example, let's check again. Check the path 2 3 3. So originally you have 0, right? Then you do bits of OR with 2 to the power 2, that is 4, right? You have 1 0 0. So what you get is 1 0 0. Then you check 1 0 0 with 2 to the power 3. So 2 to the power 3 is 1 0 0. So you are going to get 1 1 0 0. And then you have 3 again, right? So you get 1 1 0 times 3. So 1 0 0 0. So 3 is 2 to the power 3, 1 0 0 0. So you're going to get 0 1 0 0. So the odd frequency 1 is just a 1, right? So this is 1. And if you want to check 2 3 1, this path. So originally you have 0, right? Do the 2 to the power 2, that is 1 0 0. You get 1 0 0. Then you do bit size OR is 2 to the power 3, that is 0 0. So you're going to get 1 1 0 0. Then you do with 1, that is 2 to the power 1, that is 1 1 0 0. With respect to 2 to the power 1, that is 0 0 1 0. So you're going to get 1 1 1 0. So it means that the number of odd frequencies is 3, right? Because 2 appears once, 3 appears once, 1 appears once. So this is the way. So now let's look at the coding format. It's rather simple. So, but you know, how do we count this? Or just see, we just check at most 1 odd frequency in the root to leaf path. So we just need to actually check. So if you finally find the root path value is S after those operations, you just need to check S and S minus 1, right? So if S is if it contains only 1, at most 1, if it's S is 0, right? So it's nothing. If S contains just 1 bit set, for example, you have 1 0 0, right? Then you do S minus 1, you are going to get 0 1 1 1, right? So this will give you 0, right? So if this guy is 0, it says at most 1 odd frequency or 1 bit position set, otherwise not, right? So and then you can look at another example. For example, if let's use a bit position, let's see 1 0 1 0 0. So this this third position bit and fifth position bit are set, then you will get S not modulo. See, here is S and so we are going to do add. So you are going to get so this is 0, right? So this you do x minus 1, you are going to get 1 0 0 1 1, right? So you do 1 0 1 and then you do add 10011. So you are going to get see 10111, right? So anyway, it's not 0. So let's see, 0. No, here 0. So here actually it's not all. It's add. This is the 1000. So this is the sort process. So now let's write the third solution using this. I'm going to copy this part, and then I'm going to modify above so that you know the sort process. So here we have v2, and then I'm going to have originally we have 0, right? So then what we are going to do, first we get the node and the path value, right? And then we want to first update the path. So let's see, here path, let's see, first I'm going to do path, exclusive OR with node value, 2 to the power node value, right? So I'm going to do something like 1, so shift to the left, let's see, node value operations, right? And then we're going to do a check. So let's see, if not node left and not node right. So in this case means that we have a path from root up to leaf, and then we just need to check if this path is a valid pseudo palindromic one. So basically we want to check if path and path minus 1 is 0, right? In this case, it means it indeed is 1. I'm going to increment the result by 1. And otherwise, we just do nothing, right? So then we can check right subtree and then left subtree, right? So here we don't need to do anything. We just need to, so here, so we just need to add, so the s append, so the node information, and then the bitwise OR result before this one, right? Before this node right. So that is the current path state. So we'll just pass. And then if you do left, just do left, and then do pass, right? So much simpler, right? Because here the second component is also just a number, so we can also return the count. So let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So overall, if we want to see understand the last operation, so you should have some familiarity with bitwise OR operation, right? So basically here what we used is that, so if you have a 0 bitwise OR with a number, it's just itself, and then a number bitwise exclusive XOR with itself will be 0. That's what we are going to use. Actually, we want use this to check evenness or oddness, and then afterwards, so here we use also the assumption that the values are digits from 1 to 9, right? We just need to use, so at most so 10 digits, right? Or 1, because here we didn't use zeros in 1, right? So and another point is that this expression s bitwise add with s minus 1 can help us check if there's only one, at most 1 bit set, right? So if you look at the 3 solutions, actually their thought process are the same, but here originally we used large space, and then we improve from a dictionary to set, and then from set to bitwise operation. So with that said, I guess that's about it for this video. It's sort of long, especially when we do explain the third option, so we take more time. So with that said, I guess that's it. Thank you.